Remember that if your cell potential is positive, that means the reaction is spontaneous and will occur naturally of its own accord. All you have to do is make sure that you have a wire connecting your cathode from your anode, and you've created a voltaic cell. However, if your cell potential is negative, this means that you haven't created a voltaic cell. This means that the reaction is not going to occur of its own. We actually need to do something else. You've created something different. Now, how much work your cell is actually capable of doing, how much work is actually available to be used, how much energy is freely available to be used, is actually its own value in chemistry, and it's called Gibbs free energy. And we symbolize it with delta G. It also tells us how spontaneous a reaction is at a constant pressure and temperature. The formula for Gibbs free energy is delta G, so Gibbs free energy equals the negative N Fe. Or since we're staying at a constant temperature and pressure, or constant temperature and pressure at standard conditions, you can call it G naught, and you can use E naught. So the cell potential. So what do these values mean? Well, N is the number of electrons transferred, and that has no units with it, so units are not going to help us out as much this time, guys. But always remember, units are our friends. So the number of electrons transferred, that's what N stands for. F stands for Faraday's constant, and that's the electrical charge of 1 mole of electrons. And don't worry, you don't need to memorize it. It's given to you on your AP given sheet. If you look under electrochemistry, thermochemistry and kinetics, right next to it we have all of these constants given to us. Faraday's constant, right there. Very nice. It's 96,500 coulombs per mole of electrons. Lastly, E or E naught, or E at standard conditions, is simply cell potential, EMF, what we were talking about in our previous video. So given this information, we now should be able to, if we go through all the work of finding out what our cell potential is, we could also find out what our Gibbs free energy, or how much energy is available for us to actually do this work, and how spontaneous of a reaction is it. So let's do one of these. Calculate the free energy, or delta G, at standard conditions for the following reaction. So remember, delta G equals the negative number of moles times Faraday's constant times the cell potential. So let's start first by figuring out how many electrons are going to be transferred here. So if we do this, we're going to have to break this into a half reaction and make sure we've got a nice balanced half reaction. So let's break this into its oxidation half and reduction half. Gold goes from being silver goes from being silver 0 to silver plus 1, so that's going to be 1 half. And oxygen goes from being oxygen 0 to oxygen minus 2, so that's the other half. So oxygen's charge is reducing to minus 2, and silver is oxidizing to plus 1. So let me write that up here really quick. So I have my oxidation and reduction half. Let me just label those really quick. Alright, so right off the back I can see that this is not going to be balanced just yet. I've got to make sure I balance it out. And actually I probably could have spared myself a little time because I was given a balanced equation. I could have just copied that down. So it looks like I have 4 is in common between 1 and 4, so I'm going to multiply this top part by 4. Alright, and now I've got a nice balanced equation here. 4 electrons is going to be transferred, so now I know I found N. N equals 4. And since this is a multi-step problem, I'm just going to start filling it in into this equation up here at the top. So I'm going to replace N here with 4. Alright, we've got one thing down. Moving on to the next, we need to fill in F. F's a constant. We've already done that. So all we got to do is pull up our givens, which I know you really just looked at a minute ago to you, but I've been switching back and forth, so it's been a couple minutes for me. It's 96,500 coulombs per mole, so I'm going to plug that into my equation. And we'll have something that looks like this. So now all that's left is we have to find the cell potential of this reaction. So we're going to take our redox reaction, which we've already done, and we're going to look for each one of these reactions on our reduction potential chart. So we'll start with silver. Silver's being oxidized here, so we're going to look for the reverse of this. So we're going to look for silver ions becoming silver solid. So we're going to look for silver ions becoming silver solid. And there we go, silver to silver. Value of 0.8. So we're going to replace this out here. We're going to put the cell potential out here. And this is going to be the cell potential, or the reduction potential of silver. Oh, this is backwards. So let's take the opposite, because that will give us the oxidation potential. So rather than be positive 0.8, we're going to make it a negative 0.8. Alright, so that gives us the oxidation potential, or the half cell potential of our anode. Alright, let's look for our cathode. So we're going to look for oxygen being reduced to become water. And if I look on here, I can find oxygen, and it's becoming water, but I've got these 4 hydrogen here. Well, that looks mighty familiar. If we look at the original, hey, there were 4 hydrogens there too. So that's where that's coming from. So we can use that value. Hold on, let me fix this equation down here, because this isn't exactly right. Let's put in those 4 hydrogens. There, now we got something that makes some sense. Alright, so now what was the cell potential for that one? Let's look back at our table. We get a positive 1.23. And look, it's higher than silver. That's why it's being reduced. That's why it's our cathode, that's why it's our cathode. So I'm going to plug that value right here. Alright, and now we've got our half cell potentials. If we add them together, because cell potential, or E naught, equals the cell potential of the redox plus the cell potential of the oxidation. Now if you're following the original, we wouldn't have switched this value. We would have left it as 0.8, and then it would be if you're following the original equation, hold on, I'll show you both. So since we flipped this, that gives us the half cell potential of the oxidation. Because remember that this table is standard reduction potentials. So if we flip one of these values over here for the standard reduction potential, we flip one of these values and give it the negative or opposite sign of whatever it has, that's our standard oxidation potential. So that's why I flipped this for silver, because it's not being reduced, it's being oxidized. So that's why I wrote E ox naught, because it's the oxidation potential. And if I'm going to use that value, I'm going to use it by adding it to the reduction potential, so the potential of the cathode, and that will give me the cell potential. But I'll get the same value if I take the original formula I showed you in the previous video and subtract from the cathode from the anode. Subtract the anode from the cathode. Because you'll see in just a second, it's going to give us the same value. Because in the end, I'm taking the cathode and the anode, and I'm getting the same value. So I'm going to do both at the same time, so you'll watch them both by magic of editing appear at the same time. So I'm going to plug in the cell potential of the anode into both of these. And yes, there was some more editing magic there in case you missed it, but maybe you didn't. And then I'm going to plug in the cell potential of the cathode. And you see that I have the exact same operation in progress. 0.123 minus 0.8. And I get 0.43 volts. So that's the cell potential for this reaction. So I'm going to plug that into my Gibbs free energy. And now I've got an equation that looks like this. And then it's just simply plug and chug. Except my units are a little off. If I just multiplied this out, I would end up with Coulomb volts per mole. But you got to remember back. You might need to take a flashback, or you might need to look back at the previous video. A volt is a joule per coulomb. So actually coulombs are going to cancel out here. So if I rewrote it, it would look like this: 96,500 coulombs per mole times 0.43 joules per coulomb. The coulombs are going to cancel out. And my ending units are just going to be joules per mole. So once I multiply all this out, I end up finding out that delta G equals a negative 170,000 joules per mole. Let's make this a little easier. Let's change this to kilojoules just for giggles. And we find that it's negative 173 kilojoules per mole, which is the correct answer. Yay!